Okay, students. So now I want to talk about escaping the solar system. What does it take for a spacecraft to escape from the Earth? What does it take for a spacecraft to escape from the solar system? And so where this is going to lead to is a calculation of what's called the escape velocity. But before I talk about the escape velocity, I want to go back and revisit the orbital velocity. This here is the answer for the question, what is the speed of a satellite in a circular orbit around the Earth? Now, the easy way to figure out, to find this formula is to use the idea of centripetal force equaling the gravitational force. I mean, the gravitational force is the centripetal force, so they have to be equal to each other. So let's just quickly do that. I'm going to write down the centripetal force is equal to the gravitational force. And the centripetal force is mv squared over r. Now, I'm going to call the thing, the satellite, the thing that's orbiting, I'll call it M1. And the Earth is going to be M2. That's to be consistent with the notation that we're about to deal with. All right, let's keep going. So that's the centripetal force. So this has to be equal to G, M1, M2 over R squared. Okay, now you can see that the M1s are going to cancel. So what that means is it doesn't matter what the mass of the satellite is, but mass 2 being the mass of the Earth, that does matter. All right. Now, what we're after is the velocity, the orbital velocity. If I multiply both sides by r, I get rid of this r, and I partially cancel the r squared. I just get rid of the square part. All right, so I've got v squared equals gm2 over r. Now I'm going to take the square root of both sides, and I get the square root of v squared is just v equals the square root of gm2 over r. And so that's the speed of an orbit. Try to remember this one because there's going to be an interesting coincidence that happens with that. Okay. So now we know the velocity needed, the speed needed to do a circular orbit around the Earth or around the Sun. The question now is, what does it take? How much velocity, how much speed does it take to completely leave the Earth, to escape from the Earth? Or how much velocity or speed does it take to escape from the Sun? So that's what this is about. When we say that we can escape from the Earth, that means, one way of saying it is that we are unbound. We're no longer gravitationally bound to the Earth. But if we don't have enough speed, if we don't have enough kinetic energy, then we are stuck. We can't get away from the Earth, and we are bound to the Earth. So let's take a look at this idea in some detail. The potential energy of a satellite, let's say orbiting the Earth, normally our book uses the letter U, not PE, is given by this formula. So it's minus G m1 m2 over r. And the kinetic energy is 1/2 mv squared. Okay, so it looks like in this example, we're escaping from the Sun. So the Sun is mass 1. The spacecraft is mass 2. It has a velocity v. Now, here's the general rule. If the total mechanical energy, the potential energy plus kinetic energy, is less than 0, then we can't escape. We are bound to the sun. On the other hand, if the total mechanical energy, the potential energy plus kinetic energy, is bigger than 0, then we can escape. We are not bound to the sun. We have an unbound system. Okay. So looking at this graphically, we have here, this is the bound system. This is the potential energy graph of the spacecraft in the vicinity of the sun. So as R increases, you're getting farther and farther away from the sun. So let's say that you are right here, all right? This is your potential energy. Now your total energy, your total mechanical energy is whatever this potential energy is plus your kinetic energy. So if you add in your kinetic energy, now you've got this much total energy, total mechanical energy. And you are stuck. You can't get past this spot here. This is as far away as you can get. Your rockets, you turn on your rockets, you get all that speed, you burn up all of your fuel, and now you're coasting. You're going farther and farther away, but you're slowing down because you see your kinetic energy is less here and less here until finally, when you get to here, your kinetic energy is 0. At that point, you start coming back towards the sun. On the other hand, let's suppose that, once again, this is your potential energy curve here, and you're starting out at the same place, but your rocket engine gives you a lot more speed. It gives you a lot more kinetic energy. So now your kinetic energy is this much, and so now your total energy, your total mechanical energy is enough, and you never, the total energy never runs into the potential energy curve, and so you can go out to infinity. You will escape. Let's have an example. This example, I've got a rabbit, and it is launched at 20,000 meters per second. So we're talking big speeds here, but that's what it takes, to escape from the solar system. Will it escape? Assume that it starts from 150 million kilometers from the sun. Okay, so the starting point matters. If you're already far away from the sun, it's a lot easier to escape because you already have a lot of potential energy. Here's the mass of the sun. So here I am calculating the potential energy, right? In our textbook, this would have been U. So I put in my numbers. Here is G minus 6.67 times 10 to the negative 11. Don't forget, the formula for potential energy has this negative sign. We talked about that earlier. I put in the mass of the sun, which is in kilograms. I left that out. Here's the mass of the rabbit. It's also in kilograms. Here is the distance from the sun. Now, a kilometer is 10 to the 3 meters. Million is 10 to the 6. So 10 to the 6 plus 10 to the 3 is 10 to the 9th. That's why you see 10 to the 9th right there. 150 times 10 to the 9th meters. So this is in meters. And you find out, okay, the potential energy of our rabbit is, at the starting point here, negative 2.67 times 10 to the 9th joules. Now we need the kinetic energy, right? This would be K. So it's 1/2 mv squared. So it's 1/2 times the rabbits in kilograms, 3 kilograms, times 20,000 meters per second, right? That was a given. And 20,000 meters per second. Don't forget to square it, right? It's 1/2 mv squared. And you get 6 times 10 to the 8th joules. So now let's add these two answers together. The kinetic energy is here, 6 times 10 to the 8th. We have the potential energy, negative 2.67 times 10 to the 9th. And the answer is negative. Oh no, the rabbit is stuck. The rabbit can't leave the solar system. Why would the rabbit want to leave anyway? Okay, now if he had more speed, then enough more speed, and then his kinetic energy could be bigger, and then if the kinetic energy is big enough, then this becomes a positive number, and yes, he does escape the solar system. Now, one reason why I'm hammering away at this is because of the way atoms work. This is sort of an old-fashioned model of atoms. Nevertheless, this old-fashioned model gave the right answers for about 40 years when physicists at the beginning of quantum mechanics were working out the energies of hydrogen atoms. So this is still an important idea. Electrons orbit around the nucleus. Instead of a gravitational pull, it's the negative charge of the electron and the positive charge of the nucleus. That's what's providing that pull inward. And it's interesting to compare the physics of atoms versus the physics of gravity. Here is the formula for gravitational force. Here is the formula for the electric force, the electron and the proton. Okay, I was using R before, and in here this is D, but okay, if you want, you could just replace all of the D's with R, so this would be R squared. But anyway, that's not important. What's important is how similar. Look, this is G m1 m2 over d squared. Here, it's K q1 q2 over d squared. q1 is the proton charge. q2 is the electron charge. The potential energy is minus G m1 m2 over the distance. Here, the potential energy is K, charge of the proton, charge of the electron over d. Notice that the negative sign is gone, but the electron is negative. The kinetic energy formulas are identical. So because the mathematics of all of these forces and energies are basically the same, atoms and things in orbit in the solar system behave pretty much the same way. It's just the distances are crazy different. If you have an electron that escapes from an atom, that's called ionization. And so the same rules, potential energy and kinetic energy. If the kinetic and potential energies add up to a number less than 0, then the electron is stuck. But if it's bigger than 0, the electron escapes. Right. Now, let's work on figuring out just what is the velocity you need to escape from a gravitational pull from the Earth or from the sun or from whatever. So here's the process. You write down the formula for kinetic energy. You write down the formula for potential energy. You set these two things equal to each other. And the reason for that is if they're equal to each other, then when you put them together, the total mechanical energy will be 0, which is just barely enough to get past the potential energy curve, right? Because the potential energy curve approaches zero, but it never quite gets to zero. It's an asymptotic approach. Ha. So you want to do that yourself, stop the video at this point, see if you can do it yourself. Otherwise, here is the process, right here. So I'll let you look at this, but what I want you to see is the answer. This is the escape velocity. Now here's something really interesting. The orbital velocity that we figured out at the beginning of this video is v equals the square root of g m2 over r. Right? They're almost the same formula except for the 2. What do you know?